A spring, a swing, a vibrating guitar string, and even the motion of some atoms all share the same hidden pattern. They move back and forth around an equilibrium position. The object does not just move randomly, it repeats its motion in a predictable way. In this video, we will describe that repeating motion using simple harmonic motion. We will connect the position of the object to a cosine graph, define amplitude, period, and frequency, and then show how velocity, acceleration, mass, and spring stiffness determines the motion. For simple harmonic motion, the displacement changes smoothly and repeatedly with time. The equation on this slide can be read in words as displacement equals amplitude times cosine of quantity that depends on time. The displacement tells us where the object is relative to the equilibrium. A positive displacement means the object is on one side of equilibrium, and a negative displacement means it is on the other side. The amplitude is the maximum displacement from equilibrium. It tells us how far the object moves away from the center position. If a spring moves 5 centimeters to the right and 5 centimeters to the left, the amplitude is 5 centimeters, not 10 centimeters. The full distance from one extreme to the other is twice the amplitude. The period is the time required for one complete cycle. One cycle means the object returns to the same position and the same direction of motion. If the mass starts at maximum stretch, then one full period later it is back at maximum stretch again. Angular frequency tells us how quickly the cosine pattern repeats. It is measured in radians per second. It is related to period because one full cycle corresponds to 2 pi radians of phase. The picture on the right shows a vertical mass bouncing on a spring and recording its motion on paper. The recorded curve is sinusoidal, which means the displacement over time follows the same wave-like pattern shown by the equation. Next, we will see why circular motion is often used to visualize this cosine relationship. This slide shows an important visualization. Simple harmonic motion can be thought of as the shadow or projection of uniform circular motion. Imagine an object moving around a circle at a constant angular speed. If we shine light from below and watch only the horizontal shadow of the circular motion, the shadow moves back and forth along a straight line. That back and forth motion is simple harmonic motion. The reason this works is because the horizontal position of point on a circle is described by a cosine function. In words, the displacement is the maximum displacement times the cosine of the angle. Since the angle increases steadily with time, the displacement becomes a cosine function of time. This connection helps us understand why simple harmonic motion is not just any back and forth motion. It has a very specific mathematical shape. The position follows a sinusoidal pattern. This also helps explain the graph from the previous slide. As time passes, the circular angle changes steadily, but the horizontal projection speeds up and slows down. That is why the object moves faster near the center and slows down near the turning points. Now that we know displacement repeats like a sinusoidal function, let us define the timing quantities. Amplitude, period, and frequency describe the size and timing of the oscillation. Amplitude is the maximum displacement from equilibrium. On the graph, it is the height from the center line to the top of the curve, or from the center line to the bottom of the curve. It is not the total top to bottom distance. Period is the time required to complete one cycle. On the graph, One period is the time from one peak to the next peak, or from one identical point in the motion to the next identical point. Frequency is the number of cycles completed each second. If a system completes many cycles each second, it has a high frequency. If it takes a long time to complete one cycle, it has a low frequency. The relationship between frequency and period is simple. Frequency is 1 divided by the period. So if the period gets larger, the frequency gets smaller. Angular frequency is another way to describe how fast the oscillation progresses through its cycle. In words, angular frequency equals 2 pi times frequency, or 2 pi divided by period. The factor 2 pi appears because one full cycle corresponds to 2 pi radians. Once we know the position as a function of time, we can describe how velocity and acceleration change during the oscillation. The position follows a cosine curve. The velocity follows a sine-shaped curve, and the acceleration follows a curve that is opposite in sign to the displacement. The most important physical idea is this: velocity and acceleration do not reach their maximum values at the same time. When the object is at maximum displacement, it's momentarily at rest, so the velocity is zero. But the spring force is strongest there, so the acceleration has its largest magnitude. When the object passes through equilibrium, the displacement is zero. So the spring force and acceleration are zero at that instant. However, the object is moving fastest at equilibrium because it has been accelerated toward the center. The acceleration relationship says that acceleration is proportional to negative displacement. That means acceleration always points back toward equilibrium. If the object is displaced to the right, acceleration points left. If the object is displaced to the left, acceleration points right. This is what makes the motion harmonic. The acceleration is not constant. It changes in both magnitude and direction as the object moves. Now let us connect these graphs to the physical mass spring system. In this slide, we show a mass attached to a spring sliding on a frictionless surface. This is one of the clearest examples of simple harmonic motion. At equilibrium, the spring is not stretched or compressed, and the spring force is zero. If the mass is pulled to the right, the spring pulls it back to the left. If the mass moves to the left and compresses the spring pushes it back to the right. The spring force is always directed toward equilibrium. Because the acceleration is in the same direction as the net force, the acceleration is also directed toward the equilibrium. At the extreme right or extreme left positions, the mass has zero velocity for an instant because it is changing direction. But the force and acceleration have maximum magnitude there. At equilibrium, the mass has maximum speed. The force is zero at that instant, but the mass does not stop because it already has velocity. A stiffer spring produces a shorter period, so the oscillation is faster. A larger mass produces a longer period, so the oscillation is slower. This makes intuitive sense. A stiff spring pulls harder for the same displacement, so it returns the mass more quickly. A heavier mass has more inertia, so it is harder to speed up and slow down, making the motion take longer. Next, we will derive the frequency and period of a mass spring oscillator using Newton's second law and Hooke's law. We start with two ideas. First, from Hooke's law, the spring force equals negative spring constant times displacement. Second, from Newton's second law, The net force is equals to mass times acceleration. For simple harmonic motion, acceleration is proportional to negative displacement. So the acceleration becomes more strongly directed back toward equilibrium when the displacement is larger. When we combine these ideas, the displacement factors cancel and we are left with a relationship between angular frequency, spring constant, and mass. So the angular frequency is the square root of spring stiffness divided by mass. This tells us the oscillator moves faster when the spring is stiffer and slower when the mass is larger. The period is related to angular frequency, so the period becomes 2 pi times the square root of mass divided by spring stiffness. A larger mass makes the period longer, and a larger spring constant makes the period shorter. This is a powerful result because the period of an ideal mass spring oscillator does not depend on amplitude. As long as the spring behaves ideally, pulling it farther changes how far it moves, but not the time for one cycle. Now we will apply the period formula to a real example, measuring an astronaut's mass in space. This example shows a practical use of simple harmonic motion. In space, ordinary bathroom scales do not work the same way because they rely on weight. But an astronaut still has mass, and mass affects the period of an oscillating spring system. The device consists of a spring mounted chair. The astronaut sits in the chair, and the system is set into vibration, and the period is measured. We are given the spring constant, the mass of the chair, and the measured period. The spring constant is 606 newtons per meter. The chair has a mass of 12 kilograms and the measured period is 2.41 seconds. The question asks for the mass of the astronaut. The key idea is that the spring does not respond only to the astronaut, it responds to the total mass that is oscillating. That total mass is the mass of the chair plus the mass of the astronaut. So our strategy is to use the period formula to find the total oscillating mass and then subtract the chair mass to find the astronaut's mass. Let us now solve for the total mass and then isolate the astronaut's mass. To solve the problem, we start from the period relationship for a mass spring oscillator. The period is equals to 2 pi times square root of total mass divided by the spring constant. Now we can square both sides. So we get t square equals 4 pi squared total mass divided by spring constant. And then we want to find total mass. So we can multiply both sides by the spring constant. We get spring constant times t squared equals 4 pi squared m total. And then from here we get the total mass is equals to k t squared divided by 4 pi squared. And we know the total mass mt is equals mass of the chair plus the mass of the astronaut. So we can replace this here. We get mc plus ma equals kt squared divided by 4 pi squared. So from here we get the mass of the astronaut is equals to kt squared divided by 4 pi squared minus mass of the chair. Now we can substitute the values. So this is equals to 606 newtons per meters times 2.41 seconds squared divided by 4 pi squared minus 12 kilograms, and this is equals to 77.2 kilograms. So that means the astronaut's mass is 77.2 kilograms. This result is reasonable. The total oscillating mass was about 89.2 kilograms, and after removing the chair's contribution, the astronaut's mass is in a realistic human range. The important lesson is that simple harmonic motion is not only a theoretical model. By measuring the period of oscillation and knowing the spring constant, we can determine mass even in situations where weight is not easy to measure. So to summarize this video, simple harmonic motion is repeated motion around equilibrium. The displacement follows a sinusoidal function. The amplitude tells how far the object moves from the equilibrium.